All right. Well, yeah. Welcome everybody. I think we'll get started here. So for this session, we're going back to question answering. We did a series on question answering and then switched over to the conversational chatbots. So what I've got today is kind of redundant with the last session we did on question answering and RAG. But I wanted to try digging deeper into the code. So that's kind of what we're looking at today. So there's a script that the authors of RAG put together for so yeah, there's a version of RAG that you can use. RAG's retrieval augmented generation. It's a question answering framework. And there's a version of it you can use that's in the Hugging Face Transformers library. It's under Transformers Examples Research Projects RAG, and they've got a script in there for helping you apply the RAG model to your own set of reference text. And what we're going to look at, we've got a reference data set on Game of Thrones that actually comes from another question answering library called Haystack. So the script that they provide is pretty good. It's not that long. It is actually reasonably well commented, and it's kind of designed to be run on the command line. But I wanted to like dig into it deeper to understand the different steps and kind of expand it and explain them. So that's what I've got. I've got a notebook where I've taken this script and started to break it up more. To start with, I did put together a notebook where I'm just running the script kind of as is. So we can see what that looks like. So to do that, there's a bunch of libraries we need. We need transformers, the Hugging Face datasets library, Facebook's similarity search library, and then PSUtil, which I'm not familiar with. So we install those, and then grabbing the script out of the GitHub repository, Uzone knowledge dataset, and then yeah, this is the Game of Thrones dataset. It's coming from Haystack, which is put together by a company called DeepSet AI. So what the dataset is, it's 200. I think it shows it down here. Yeah, 183 articles. They're all taken from like regular Wikipedia, so not like a specialized Game of Thrones wiki, but just standard wikipedia.org. So there's a little prep work to do, not much. We read in all those articles and basically take the file name, use that as the title, and then append the text for the article. So we've got a list of 183 titles. You can kind of see them there. And 183 articles. And then we spit those out to a CSV file. And the script expects that the data is presented in two columns, a title column and a text column. So put the titles and the articles there. And then that's all the data set prep we have to do. The script takes care of the rest of it. So we will go into the steps more, but I thought it'd be fun to look at some of the outputs from the script. Yeah, so it takes, let's see, 270 seconds. So it takes like 4.5 minutes for this guy to run. Basically just specify the path to that CSV file that we just created, and you can put a question on the command line. So who is Arya Stark's father? And it gets this one right, Lord Eddard Stark. And then I went and found like a trivia. Yeah, Game of Thrones quiz online. So tried putting in some of these. This one's a little harder. At the beginning of the series, how many children do Ned and Catelyn Stark have? And then the answer they gave is that they have 5 children: Robb, Sansa, Arya, Bran, and Rickon. Doesn't count. They're not counting Jon Snow. So I'd say 5 or maybe 6. And Rag said 6. So hopefully that's because they're including Jon, not just a guess or something. Who was the first character in the series to be called King in the North? It's Robb Stark, but it gets it wrong. King Caspian. I don't think there's a character named Caspian in Game of Thrones. I feel like that's like a C.S. Lewis thing, maybe. Like maybe it's pulling that from its parametric knowledge instead of the reference text. So yeah. Let's see. Let me look at the. Yeah, that one took 5 minutes. We'll see in the other script that I've got. There's some setup that happens, but then the actual question answering piece where you feed it through this whole system is actually taking about 3 minutes. So it's pretty slow. Yeah. All right. One more. Which cast member did Kit Harington marry in 2018? Correct answer is Rose Leslie. Rag said Lena Headey, she plays Cersei in Game of Thrones, so that one's incorrect too. I didn't bother to go look at whether this information is actually in those articles, so could be that it's an unfair question. Didn't get this one right either. Who succeeded Robert Baratheon on the Iron Throne? So Stannis Baratheon. He would have liked to have succeeded him, but it was Joffrey. So, yeah. So, it's giving out sensible answers, but a lot of incorrect ones. I think I might try, if it doesn't turn out to be a ton of work, which, it seems like maybe it would be. But it could be interesting, I think, to try scraping an actual Game of Thrones wiki. I'd imagine I might have some more detail to it. And maybe if that was added to the reference data set, it might do better. I could see. All right. So this is a notebook I'm planning on sharing, but it's still under construction. But I'll walk us through what I've got so far, which it's mostly there, but not all the comments and illustrations are done, and it's actually not working correctly at the moment. So definitely still some work to do. So let's start with what it does with the text, right? So a little more about, Haystack. It's one of their tutorials. Right, they need to be broken into smaller. So I've got the data set up already. And one of the first steps that script does, and I moved it to the appendix because I figured it's it's not that interesting, but right. So this is that same code for reading in the articles. But then the text, the articles need to be broken up into chunks. And the way they do that is they split the text on white space to kind of tokenize it into real words. And then they break it up into 100-word passages. So that's not the same as 100 tokens, right? Like each word could break into multiple tokens. I'm sure a lot of them do. So the actual token length, sequence length of those passages is going to be significantly longer. But I think they do this as a way to address the 512 token sequence length. So they're trying to cut up these passages so that they fit. And you need to be able to fit both the question and the reference text into the input sequence. So that's what this is all about. Yeah, so they split it on white space, grab 100 words at a time, and then rejoin them with with just a single space. So they cut out any extraneous white space. And then the final data set, it was 183 articles. Let's see, I've lost the output here, but it splits it into something like 4,500 passages. So data set gets a lot bigger once you chunk it like that. And I think I've got down here. Yeah, there we go. So we're using the a lot of this is based on, and I think, like becoming more, to use the RAG framework, you kind of need some familiarity, excuse me, with the Hugging Face datasets library. So they've got this library. They managed to grab the Python name datasets. Pretty impressive that they were able to secure that. But yeah, so that's datasets is their library. It gives you access to a ton of text datasets, but it's also kind of the building block for managing the reference text for RAG. So a lot of what I've had to do in order to make sense of this is like better understand the datasets library. So this load dataset function is one they've defined. Normally what this would be is like the sort of like the path to one of the curated data sets in their library. But if you say CSV, then it knows to pull in from a local file. So give it the path to our Game of Thrones chunked data set, tell it what the delimiter is, it's tab separated, and tell it the column names. So that loads it into this dataset object. The datasets have this notion of splits. So by default, it loads everything into the train split, which we don't really, for this, we don't need any splits. So you can dereference that so that the dataset is just the what's inside the split. And you can take a peek at one of those passages. So this is from the article Game of Thrones. And you can see it's taken from, I picked passage 100 arbitrarily. So this is, you can tell this is taken from kind of the middle of one of the articles. All right, so that's pretty basic stuff. I think the more interesting pieces are the retriever and then the generator. So the retriever is built using this architecture, dense passage retrieval. Also a Facebook creation, and it uses embeddings to represent the reference texts, and then does sort of a similarity search on those embeddings to pull out which reference articles are the most useful for answering the question. So it takes in fact, let's take a look at the, we already have some good notes here on this. Zoom in a ton so we can look at the illustration. Yeah, so these are the notes from the last session on DPR. So it's actually got two encoders. It's got a question encoder and a context encoder. It looks like from the GitHub repository for DPR, they say that the default is that it uses BERT base for the encoders. So nothing particularly special there. I did think it was interesting that they trained a separate encoder for the question and the context. I'd be interested to understand that better and maybe try seeing, if you encode the same piece of text with the question encoder and the context encoder, I'd be curious to take the dot product of those two resulting embeddings and see how similar they are. Presumably they're different. Otherwise, they they could just use the same encoder for both. Yeah, so you encode, in order to do the retrieval, you encode the question, and then all of the contexts have been previously encoded. This is kind of showing the training methodology. But the search methodology is that you'd have all of the contexts encoded already, and then you take the dot product between the question embedding and all of those encoded contexts, and then find the most similar ones. So I think there's, right, so here's kind of the RAG architecture overview that shows that. So there's the query encoder, multiple, I guess this is showing kind of the yeah, this is the search. So you get the query embedding, and then you do k-nearest neighbor search. They're saying, they're calling it maximum inner product search against all of those document embeddings to find the best matches. And then we did figure out that that's to identify which articles to use. Once you've identified the context that you want, or that it's going to use for answering the question, it goes back to the original text. So the DPR embeddings aren't what's sent into the generator. They're just used for finding good reference text. So what's next here? Yeah. So I thought it's interesting to me to point out this process of embedding passages of text, has been around for a long time. I studied this a lot in my last role, traditionally called topic modeling, where you use some algorithm to create a vector representation of a document. So TF-IDF is the kind of the most basic version of that, but it creates really long vectors. Latent semantic indexing does a little more feature extraction and creates shorter embeddings. So there are other techniques for this, but it's now everything's BERT-based. So presumably DPR outperforms simple TF-IDF and LSI. So because DPR is using a BERT-based encoder to create those embeddings, it's actually got two steps, right? The text needs to be tokenized first, and the tokens are then represented by their IDs from the vocabulary, and then there's the encoding step that actually feeds those sequences of tokens into the BERT encoder and generates that embedding. All right. So the library, or the classes that are used for this. So there's the DPR context encoder tokenizer. There's a fast version, and the model name. I was hoping to find more about the meaning of this, but there's no in the Hugging Face models library. There's no model card for this guy. It's yeah, it's empty. It's popular. It was downloaded 3,800 times last month, but they don't have any additional explanation of what this model is exactly. I think multi-set. So let's see. Yeah, the options are right. Single NQ base or multi-set base. NQ is a data set. So I'm guessing that this one is maybe based off just the NQ data set, and then this one's maybe a combination of multiple data sets. But basically, it's BERT base that's been fine-tuned for similarity search. So load the tokenizer, and right, and we can Yeah, this is interesting. It tokenizes the entire data set all at once. I think I've usually done it in a for loop, so it'd be interesting to, yeah, maybe switch to this methodology here. But something I'm kind of curious about, and maybe we could figure this out right now. The tokenizer takes in both the title and the text, and I have no idea why. And I'm curious too. The other time I've seen something like this is like if you're doing question answering, then you feed it the question and the reference text separately, and it puts an SEP token in between the two. So that would be my guess as to what this is doing. But yeah, it seems a little strange to me that they would do that. I wonder if that it's like, does their, yeah, I mean, this doesn't show for the context encoder, which is what we're looking at right now. It doesn't show like putting in anything besides the reference text. There's no title. Yeah, so kind of an outstanding question that I've got.
Yeah, I don't know what they do here, but I assume that, and I've seen in other places, that appending the title of the article is like a very good piece of reference for what the article is about. Basically, it tends to help.
Nice. Okay.
If your article is about Abraham Lincoln and the first word can be Abraham Lincoln rather than this person was born on blah blah blah. So they might be doing that. I don't know.
Yeah. Okay. Yeah, and then I guess it would make sense that by using the SEP token there, it's kind of highlighting like this is the title, or it's separating it as like a separate piece of information that BERT might give more weight to. So yeah, if it's saying like the title is really valuable, then so maybe the SEP token.
Yeah, it might just be a holdover from how they trained the DPR as well. Like if the DPR was trained using title, SEP, then the content, they might just want to stick to that formatting. So they might be doing that.
Yeah, so I guess that makes me wonder, can you skip the title? If your contexts don't have a title. Yeah. All right. So we get the input sequences. They've all got to be padded. Looks like the longest sequence was 298 tokens. So, right. So that leaves, it's interesting. This is incorrect. No. Yeah, so if the sequences are all 298 tokens, then that leaves 214 tokens for the question. Is that right? No, that's right for the generator step. Yeah, what occurred to me there is for DPR, the question is encoded separately. So, yeah, so the context encoder set yeah, fully 512 token input. But the maximum in this data set is 300, so that's good. It fits. All right, logging, loading CUDA for the for transformers for the encoding. Okay, so we've got the tokenizer. We've done that step. Next one is the DPR context encoder. And so again, we're using this multi-set base. So load that, move it to the GPU, and then we can gather all of those embeddings. Okay, good. I was worried from the last cell, did I lose my output? Yeah, so that doesn't take too long. It looks like 40 plus seconds to embed 4,500 passages. Doing it in batches. So this is basically like feeding text through BERT. It's the same process. You've got to batch it because of memory limitations, right? So let's see, what did I use? I used a batch size of 16. Yeah. So from the outputs, take the pooler output. That's the CLS embedding, and then bring it back over to the CPU. Add it to the list of results, and then since we did it in batches, we've got to concatenate all those back to a single matrix. So we've got 4,500 embeddings now, context embeddings. Cool. So the next thing they do is they use the Facebook similarity search library to index these embeddings. So if you've got a GPU in the mix, you can do brute force search on these vectors pretty fast. I did some benchmarks actually on using the brute force search implementation from the FAISS library. I used a vector length of 300 for this, so it's they're shorter. So I guess it would grow quadratically with the vector length. So maybe 4 times, multiply this by 4 to get to 768, a little more than 4. So with a V100, that's this green line. If you got like 10 million vectors that you're searching through, then you can get responses in, let's see, 10 milliseconds, 20, 30, 40, 50. So under 100 milliseconds with k equals 10. So I don't think the FAISS, like actually using an approximate nearest neighbor technique is necessary here. Yeah, and I kind of talked out of turn there with so the FAISS library. It's got a great implementation of brute force search on the GPU. It's very efficient, but it was mainly published to provide techniques for indexing to speed up search on really large data sets. So I imagine this became useful when they did the training. If they're training on like all of Wikipedia, then and they've got to break it into sub passages, then maybe there's even like billions of embeddings that they're trying to search through. So at that scale, indexing makes a lot of sense. So you could actually, when you specify your index type, you could just use, they call it flat. So you could say flat inner product. All right, so install FAISS library. And then they use, in their example script, they use a technique called hierarchical navigable small worlds. Little like fun bit of history and trivia is like the authors of this library published it in part to publish their approximate nearest neighbor approach called product quantization, I believe. Yeah, I wrote a blog post on that actually. But I think they were like, after they published that, they were kind of beat soon after by this HNSW approach. So they added that to the library as well. And that's what we're using for the example. So using a face index, pretty straightforward. You call train on the embeddings matrix. I'm guessing what this does is like pull out whatever information it needs from the data set in order to build the index. But then the actual indexing happens when you call add. I was missing that step at first, and that was giving me a ton of trouble. It was actually like crashing when I tried to search the index because I hadn't added these, actually added the embeddings to it. Yeah, so then we can do an example query. Something I realized here that I kind of did wrong is I took a query from the embeddings matrix. So I guess that's relatively reasonable. But if you wanted to do your own kind of custom search here, you would use not the context encoder, but the question encoder, right? So maybe I'll add that to this example. But yeah, just to test it out, I grabbed passage 100, used that as the query, and you can just call search, returns back the distances as well as the indices of the matches, the 3 nearest neighbors. So it correctly comes back with passage 100 as the closest match. So it's saying, it's closest matches itself. And then passages 99 and 101 are the next 2 results. Yeah, and then you can see how these are fairly good. Actually, the previous example I had up here was a little more obvious because it was information about the reception of an episode, and so it gave some passages that also talked about the reception and like how many people watched the episode. So I guess we can take a little look here though. Assassination attempt. Okay. Yeah. So I guess, one way to like interpret this is like it pulled as the next best results. It took the articles immediately surrounding 100, right? It said passage number 99 and passage 101 were the closest matches. So that makes sense. And it has no, in doing the search, it has no knowledge of the order. So it's not leveraging the fact that these occurred next to each other. It's just doing that inner product search. So yeah, seems like a good validation of the method there. All right. So once you've got the index, you've got to add the embeddings and the index to this Hugging Face datasets object. And that was kind of tricky. I had a tough time figuring out how to do that properly, but I think I've got it. First, you need to add the embeddings to the dataset. So now we've got title, text, and embeddings. And then you call add face index, specify the column where the actual data is, what you want the index to be called, and let's see. I don't see any reference to the index, so embeddings. Yeah. All right, I'll have to look at that. It seems like I've got some kind of mistake there. I wonder, maybe what this function does is actually generate the face index for you based off of the embeddings that you specify. I think that's probably what's going on here. I bet what happened is I couldn't figure out how to specify my own index. Is this generating? Is this, yeah, creating a new face index? Obviously not taking the one I created. I do have a bug in here somewhere because the results I'm getting are pretty bad. So maybe it's hiding there. Okay, yeah. So after creating that index, you can retrieve it back out. I did another search. So yeah, I think it created its own index, and I was kind of testing out the one it created here. So, all right. Yeah, so that's it for the DPR step. I think that's kind of the, to me, that was the piece that kind of required the most explanation. You know, there's the most sort of added detail that's going on there. But then once you've got that, the rest is pretty straightforward. You're kind of just handing things off to some RAG classes. So we've got the RAG retriever. Yeah. So something interesting to me here is like the retriever is what's going to actually, you know, do the DPR, right? It's gonna take the question, encode it with the question encoder, search against our context embeddings, find the best matches. But I don't entirely see the connection between the two. So we're giving it our index data set. This is, you know, what we just created in the last section. It's got all the context embeddings. It's got an index for searching the context embeddings. But yeah, it seems like it must, like this model name must somehow just imply the use of the other one. Um, let's see if we can see if there's a model card for this guy. Nice. Paste, question encoder. Yeah. Question encoder or retriever are based on DPR question encoder's single NQ base. So that could be what's going wrong here. Is like I use the multi-set model for encoding the contexts, but I think what this is saying is they use the single NQ version. And then they're using Facebook BART large. That's interesting. I wonder if that's why it takes 3 minutes to run. Wiki DPR QA dataset and in fashion. Yeah, so in this example, they're kind of cheating in that they're using a well, not cheating, but there's a data set that is sort of associated with this model. So instead of showing you all those steps for kind of preparing the data set, they're able to just, you know, use dummy data set equals true. It's kind of a small subset of Wikipedia. All right, so I think I'll put a note in here about that. It's a model card. And then model card says that it uses single NQ model for the question encoder. That's what they called it. So I'm using multi-set. On the other hand, I feel like that's what they did in yeah, all right. So the context encoder, tokenizer, RAG example args DPR context encoder model name. So we can look at their default for that. Yeah. So I'm not crazy. That's what they said as the default. And when I run their script, it does reasonably well. It knew who Arya Stark's father was. My version currently gets that question wrong, so I feel like I've got something going wrong. But anyway, moving on. So the RAG retriever does the DPR bit. And then we need the RAG tokenizer, which yeah, so I guess a question I've got here is whether it's like the tokenizer needs to encode the tokenize rather. I won't say encode since we're using that elsewhere. Needs to tokenize the question in order to do DPR, and it needs to tokenize the input to BART. And those have got to be different tokenizers, I would imagine, because DPR is using BERT base, which has its own vocabulary, and then the generator is using BART large, so that's probably got its own vocabulary as well. So tokenizers have got to be different. So that's something I want to give into them. Putting a single tokenizer, is this only used for tokenizing the input to BART? How are the questions being tokenized? Actually, I think I already know the answer to that, because when we go look at an example, there we go. Okay, so it's got like a special question encoder method. So it looks like it probably is using both. Looks like it probably includes two tokenizers, and the question tokenizer is accessed with question encoder. All right, so we need the tokenizer, and then here's the real, well, it's the generator. So it needs the retriever specified to it. So that's how this guy is going to be able to do the DPR search. So this is this encompasses everything. It's got the generator, but it also has a handle to the retriever. Wonder how long that took. Is it still there? Yeah, 78 seconds, 2 gigabytes to download the BART large model. It's a beast. All right, so yeah, so here's what the question asking process actually looks like. So you've got to take your question string and first tokenize it using the question encoder tokenizer, and then you can pass it to the generate function. So model is this RAG sequence for generation. I don't know why they called it that. That's another question I've got. Like, why isn't it? Why isn't it called what would it be called? RAG generator. I don't know. RAG sequence for generation. All right, so tokenize, and then this does, so everything's hidden under here, right? It's got to take our question tokens, do the DPR search, get back its reference texts, and then retokenize the question and the references, send those into BART, and then do all of its that marginalization step to generate its answer. So what it spits back is the answer, but it's in token ID form. So we need to decode. And here, decode means like take the token IDs and translate them back into actual like string tokens. And then we've got our actual generated string. So who is Arya's father? Rhaegar Targaryen. So that's wrong, and the script gets it right. So I've got some issue in here somewhere that I still need to root out. All right. Yeah, so obviously still some to-dos here. But hopefully that gives you a little more detail on how the code actually works. Have anything else I wanted to cover? We kind of addressed this, title and article. I do want to add diagrams. Yep. All right. Well, yeah, if there's no questions, I think we'll wrap it up there. So thanks for watching, guys. See you next time. Have a good one.